For thousands of years, people sought a method to compute areas bounded by curves. They had very little success. The first almost successful attempt was done by Archimedes in the 3rd century BC. Archimedes, one of my heroes, discovered a method to approximate the area of an irregular shaped surface by looking at areas of known shapes, triangles, rectangles, etc., within that shape. He called his method computation by exhaustion, since he would continue to fill areas in with smaller and smaller triangles and rectangles until he had an approximation of this irregular area. In fact, he used this method initially to find the area of a circle. Unfortunately, a limited number of copies of his book, where he explained exactly how to do this area computation, were printed, or written actually. There was no printing in those days, and it was very, very difficult to obtain a copy. In the 14th century, scholars located a copy of one of Archimedes' books and began using the method of exhaustion to obtain areas in a very precise manner. It's interesting to note that because of the lack of printing and because most of the great works of ancient Greece and Egypt were kept in Alexandria, which for much of the Middle Ages was under the control of the Muslims, Christian Europe had little access to this. And many, many mathematicians and scientists floundered because they lacked information that had been discovered 2,000 years before. And it wasn't until the 14th century when they began to tap into the knowledge of the ancients. The creation of calculus in the 17th century provided an opportunity to find the area under a curve or between two curves. The antiderivative was created just as we created the logarithm, just as we created the square root, just as we created division. Because, as I've said in previous lectures, when you create an operation such as addition, you also create its inverse operation, subtraction. Multiplication, you create division. Raising to the second power, we create the square root. Taking a base to any power, we create the logarithm. We've created the derivative. Actually, Newton and Leibniz, we didn't do it. And we have to have an inverse operation. That inverse operation is the antiderivative, kind of like the TV quiz show. I give you the answer, and you tell me the question. I give you the answer to the derivative, and you tell me the original function for which it is the derivative. This is the antiderivative. Let's take a look at an example. We have the derivative of 5x squared is 10x. And again, in our first lecture on calculus, we did not spend a great deal of time talking about how I got the derivatives. We just talked about the definition, and then we indicated here were some derivatives that seem to match what they should do. But the derivative of 5x squared is 10x. Okay? Now, if I knew the 10x and I wanted to find out what function did I take the derivative of to get the 10x, I would take the antiderivative of 10x. You say, well, I know what that is. It's 5x squared. Almost correct. The reason it's not actually 5x squared is, remember that the derivative of a constant is 0, because a constant does not change. And since the derivative measures change, if we have no change, we have a 0 derivative. So therefore, that 10x, for which we want to know the antiderivative, could be 10x plus 0, meaning that the antiderivative of 10x would be better written as 5x squared plus c, where c is what's called a generic constant. It could be any real number. It could be 0. It could be 4 million. It could be 0.01, but it is a constant. Now, using this antiderivative, we can find the area. But the first step before we do that is to create a symbol, because we can't just, antiderivative is too much to say, and we need a symbol for that anyway. And what they created was a symbol and a word called the integral. And the symbol appeared to be a stretched S. So we would say more correctly in modern symbology, the integral of 10x dx, meaning we're integrating the function 10x with respect to x, equals 5x squared plus c. You might say, well, we know it's 10x, and therefore, what do we need the dx for? Well, quite frankly, in more advanced calculus, we deal with functions of more than one variable. Just as, for example, admission to a college is simply not based on your high school GPA. It's based on that, plus scores on SAT or ACT, activities, essays, etc. So we have functions of many variables, and in more advanced calculus, we need to indicate when we are integrating what the integration variable is. So to prepare for that, it's written this way. The integral of 10x dx equals 5x squared plus c. Now, this is called the indefinite integral. It's indefinite because we get a family of functions, 5x squared plus c. C could be anything. There's an infinite number of possible functions, all of which are 5x squared plus a constant. We can generalize from our knowledge of derivatives to state that the integral, the indefinite integral, of any function of the form ax to the n, where a is a real number, constant, and n is an integer, and a positive integer at that, in terms of what we know so far, it turns out n can be any real number. We have the integral of that with respect to x is a, the constant, over n plus 1, one more than the original exponent, times x to the n plus 1 plus our friend c. So therefore, any function of this type can be integrated, and we can find the function whose derivative is the function we started with. Now, how can we use this to find the area? Well, let's begin by defining a function f of x, just a general function, and we have this curly kind of curvy function that's f of x. And we look at values of x at a and value of x at b, and we say, okay, let's define the area under that curve, between the curve and the x-axis, between a and b. You might say it's the area bounded by the x-axis, x equals a, x equals b, and y equals f of x. Now, since a is a function of x, you notice as b would go to the right in our diagram, the area would get larger. So the area is obviously a function of x. We can talk about dA dx, the derivative of a with respect to x, where we're looking at the change in a if x has a very small increase, a exceptionally small amount of increase on x. And by examining the picture, we can see that if we moved b over just a little bit, that salami slice distance, that indeed the addition to the area would be y, the height of the function at that value of x. So what we're saying is that dA dx, the derivative of the area under the curve with respect to x, is equal to y, the value of the function at the very end. And therefore we write what's called the definite integral. And that is the integral from a to b. Notice we've added these little small letters on our integral sign. That is a definite integral from a to b, from x equals a to x equals b, of y dx. So we could find the area between a curve and the x-axis for two given values of x by simply integrating the function and evaluating that function at x equals a and at x equals b. If we wish to find the area under the curve x squared, y equals x squared, we've looked at that, we know it's a parabola, and we were concerned with the area between that curve and the x-axis between x equals 0 and x equals 3. We would integrate the integral from 0 to 3 of x squared dx. Now we know that the integral of x to the n dx is x to the n plus 1 over n plus 1. N plus 1 is 3. So we're left with x to the third over 3. And we evaluate that at 0 and 3, subtract to get the difference, and that difference is the area. Well, x to the third, when x is 3, is 27, and 27 divided by 3 is 9. When x is 0, 0 to the third is 0, divided by 3 is 0, and 9 minus 0 equals 9. So the area under the curve y equals x squared between 0 and 3 is equal to 9. You may ask, what happened to the c? Because when we looked at the integral, it was no longer a c. Well, we don't need it, because we actually have 9 plus c and 0 plus c, and we subtract 9 plus c minus 0 plus c. The c's cancel out. So we don't use the c for the definite integral. We only use it to indicate when we are taking the indefinite integral, simply asking what function did we take the derivative of to get the function we're starting with? When we're looking for the area under a curve, indeed, we don't mess around with the constants. We just integrate as indicated. So to find the area beneath the graph of y equals x to the third, that's a graph we've seen in previous lectures. And we wanted to find the area under that curve, or between the curve and the x-axis, from x equals 1 to x equals 3. We integrate the function x to the third dx, and we get x to the fourth over 4. When we evaluate this at 1 and at 3, we get 81 fourths minus 1 fourth, which is 80 fourths, which is 20. So the area under this irregular shape, that is bounded by two horizontal line segments, two vertical line segments, at x equals 1 and x equals 3, the horizontal line segment of the x-axis from 1 to 3, and the curve y equals x to the third, the area of that irregular shape is exactly 20. And I think it's hard for some people to understand that we have this irregular shape. Yes, it has a very precise area, and that this method, which seems sort of abstract, can actually create real answers that are true. In fact, a personal experience, when I got out of college, I had a temporary job as an assistant to a plant engineer, and he asked me to find the volume of various tanks if the liquid in those tanks was at various levels. That is, to calibrate the volume. And volume is similarly found with integrals. Well, he didn't trust me because I was a recent graduate of engineering college, and he sent off to the company to get a calibration chart. Meanwhile, I got out my book of integrals and figured out how to do these irregularly shaped tanks, got some answers, gave it to my boss, and he was amazed. I was right. But more amazing, I was amazed that I was right, because throughout my years of taking calculus in engineering school, it was just answers, and the answers were right if they agree with the back of the book. But we never had to integrate anything to find an area or a volume that meant anything. And here I had done it, and it was correct. And it's really nice to know, so I can pass that along to you to indicate this really works. The definite integral method for computing the area under a curve was first developed by an Italian mathematician named Bonaventura Cavalieri. Cavalieri had been a student of Galileo, a very famous mathematician and scientist. He looked upon his work, that is, Cavalieri did, as geometric, because in those days, people who worked in mathematics worked with geometry. This was before analytic geometry allowed algebra and geometry to be mixed. That turned out to be in 1637, of course. We talked about that year and the works of René Descartes. The definite integral is used to define the natural logarithm. I mentioned the natural logarithm. We talked about logarithms. This is the logarithm using the base e, the number that Euler said was the natural base. And the way we do this is we simply take the integral from 1 to a being the number for which you want the natural log, of 1 over x dx, because the integral of 1 over x dx is the natural log. And of course you get the natural log of a minus the natural log of 1. Where's the natural log of 1 in the equation on your screen? Well, let's see. The natural log would be the power that I must raise e to get that number. What power do I raise e to get 1? 0. So the log of 1 is 0, and of course, therefore, the natural log of a minus 0 is the natural log of a. There are many useful applications of the definite integral. In statistics, integration is used to find specific areas under probability curves, such as in the normal distribution. The numbers in most statistical tables are obtained by integration. Now they're attained, through the use of computers, but back in days before calculus computers, pure integration was used to find these areas to demonstrate certain probabilities. In physics, there are many quantities that are calculated using integration. One example is work. Work is the integral of a force applied over a distance. So we take the force, we multiply it by the distance, and integrate it over the distance, and that is work. There are many other areas, but that's just one example. If the change in population over time for a country or a city or a location is a function of time, that is, if the change in population is a function of time, the integral of that function over a number of years will give you the total population, or the total population growth, depending on how you define the beginning time. So there are many, many uses for integration. Well, we had calculus in the end of the 17th century. We had the derivatives to help us measure change. We had integrals to allow us to find areas and ultimately volumes and be used in physics and other areas, natural sciences, social sciences, etc. But there was a need for something else, because as humans advance, there are always new needs in terms of mathematics and in terms of the sciences and, of course, in technology. Well, what there was a need to do was to take functions that were not polynomials, exponential functions, trigonometric functions, and be able to write them more simply, or at least to compute them, so that if we wanted to find, for example, the square root of some very strange number, we could do it without getting involved in some crazy function that was very, very difficult, would take hours to work upon. And a method was found. This was called the power series. And the power series was developed to approximate various types of functions with a polynomial. Remember, polynomial is a series or a sum of monomials, which are constant times x to a positive integer power divided by some number possibly. Or simply that the coefficient divided by the number would also be a constant. So basically, if we took a series or a sum of those, we would have a polynomial. The question was, can we write a polynomial to approximate a function that's not a polynomial? Well, and again, I use the word series twice. I should mention specifically that the word series means the sum of a sequence of terms. The terms of the polynomials, or the terms of the power series, the polynomial that was a power series, were various monomials. The first power series was developed by Brooke Taylor in 1715. So you can see this didn't come very long after the creation and the public knowledge of calculus. Unfortunately, Taylor died at the age of 46 with his work unfinished, but it was completed by Colin Maclaurin. And in fact, today, both their names are attached to very, very popular, at least popular in calculus classes, power series, the Maclaurin series and the Taylor series. Maclaurin published his work, which finished up Taylor's work and his own work in 1742. The ironic fact is that the Taylor series and the Maclaurin series, which we use today, were not developed by Taylor and Maclaurin. They both did work on power series, but the actual specific work on those two types of series was done by Johann Bernoulli, one of the members of the very famous Bernoulli family, which we'll see again. As been stated in earlier lectures, the person who gets credit for some mathematical discovery or invention, or the algorithm to solve a certain type of problem, in many cases is not the actual person who did it. And a lot of this has to do with politics, and a lot of this has to do with wealthy mathematicians taking advantage of their students. But that happened years ago. Today, that probably wouldn't happen, I don't think. But certainly in the 1500s, 1600s, and 1700s, and probably into the 1800s, many times the name on the product was not the name of the person who created that product. But that's for another course. Maclaurin series are simpler than the Taylor series, so let's examine two of those Maclaurin series. And the first one is the Maclaurin series for e to the x. This would allow you to use a polynomial to approximate e to some power. Okay, so if you want to know what was e to the 3.78, you could do that very quickly by plugging in 3.78 for x once you had the polynomial series that would allow you to approximate e to the x. And that Maclaurin series for e to the x is 1 plus x squared over 2 with a exclamation point after it. We'll talk about that. Plus x to the third over 3 with the exclamation point, and so on and so forth. And the question was, how much patience do you have? How much time do you have? How many terms do you want? Because obviously the next term would be x to the fourth over 4 exclamation point, etc. What does that exclamation point mean? It doesn't mean that you yell the number real loudly. No, not at all. It's called the factorial. So for example, 3 factorial would be 3 times 2 times 1. That is, we have all the positive counting numbers, positive integers. Factorial will be that number times the next number down, the dot, until you get to 1. So 10 factorial would be 10 times 9 times 8, all the way down to 1. And these numbers get quite big. I might add that, for example, 35 factorial, which happens to be the number of ways you can line up 35 people in a straight line, is 100 times larger than all the drops of water in all the oceans of the world if the Earth was a sphere of water. I had to prove that once, and it's true. So these factorials do get very large very quickly. By the way, 0 factorial is defined as 1, which makes no sense because 0 factorial, again, should be 0, but otherwise things don't work. So all the other factorials are fine, and to use it properly, 0 factorial must be 1. Well, let's go back to our power series for e to the x and see how we would use this to find e to some power. If we use the power series to evaluate e to the 1, that is, we want to know what is the value of e. And since we know approximately what it is, actually we know it's in many places, let us use the first 6 terms of the Maclaurin power series to do this. E, or e to the 1, would be 1 plus, we replace the x with 1. 1 plus 1 plus 1 squared over 2 factorial, plus 1 to the 3rd over 3 factorial, plus 1 to the 4th over 4 factorial, plus 1 to the 5th over 5 factorial. Or 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1/20. Notice if we added a 7th term, it would be very small. If we added, a few more terms, they would get progressively smaller, rapidly smaller. How accurate do you want to be? How patient are you? How much time do you have in the days before calculators? Well, it turns out that if you use this method, the sum of those 6 terms is 2.71666, etc. We know that E is 2.7182818, etc. If that's not close enough, guess what? Stick on some more terms. If you have the time and nothing better to do, or again, you want to get out doing chores, and you want to use the first 100 terms, you would get very close to E to quite a few decimal places. But basically, if we're just concerned about evaluating a number to the 100th place or the 1000th place, it would not take many terms to do that. So basically, you define your precision, and we define how many terms it will take to get that kind of precision. Let's go ahead and go to the TI-83 and demonstrate graphically how this power series works. This is the equation editor for the TI-83. We have 2 equations in the editor. Y1, which is the first 6 terms of the Maclaurin series for e to the x, and Y2, which is e to the x. Let's graph it. First, we'll graph the Maclaurin series. Notice it comes below, goes along the x-axis, and then rises up, and here comes e to the x. You'll notice that in this area here, they are divergent. And also, as you get towards the top of the screen, they begin to diverge. So basically, between x equals -2 and x equals +2, our first 6 terms do a very good job at approximating e to the x. For numbers beyond 2 or beneath -2, we probably either want to add more terms or use another method. The second function that we will use Maclaurin series to estimate or approximate is the sine of x. We'll talk more about what the sine means and how it got its name in the lecture on trigonometry. But certainly it's a function, a name that you've heard before. And the Maclaurin series for the sine of x is written as sine x equals x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. And I'm sure you can fill in the rest. The terms you'll notice are odd powers of x divided by those odd numbers factorial. Now, one of the things we must understand is in using calculus, when we talk about trig functions, we cannot use degrees. The reason for that, I will leave up to your calculus professor. I know the answer, but I don't want to get involved in it because it would be too involved. Suffice it to say, we must use radians. Now, what are radians? If you haven't taken a trig course, radian is just another way to measure angles. We know that the circle has 360 degrees, and that goes back to the Babylonians, who liked the number 360. They like numbers that involve 6 and 60. And we're going to say that 2 pi radians equals the complete circle. That is, 2 pi radians equals 360 degrees. Thus, pi radians is half a circle, 180. Pi over 2 would be half of that, 90 degrees. Pi over 6 would be 30 degrees, and so on and so forth. In fact, it's very nice that the Babylonians picked the number 360 that is divisible by so many numbers. But that's another story. Basically, let us use the power series, the Maclaurin series for sine of x, to find the sine of 30 degrees. And simply using the first 4 terms, as we saw before, down to the x to the 7th, we find out that the sine of 30 degrees, or the sine of pi over 6, is 0.5000213. Now, the actual sine of 30 degrees, or pi over 6 radians, is 0.5. Now, if 0.5 is not close enough to 0.5000213, then guess what you can do? You can add more terms, and the more time you have, and the more patience you have, and the larger piece of paper you have to write very, very long decimal numbers, you can come closer. Because notice that the terms of sine are alternating in sign, S-I-G-N, positive and negative. So we'll add a little bit and we'll subtract a little bit. We'll add a little bit and subtract a little bit, and basically we will come very, very close to 0.5. If we had an infinite amount of time, with an infinite amount of terms, because the Maclaurin series really is an infinite series, we would come to 0.5. But we don't have time for that. But we do have time to go to the TI-83 and to see graphically how this polynomial, this Maclaurin series, approximates the sine of x. Here is the equation editor. In y1, we have the first 4 terms of the Maclaurin series for sine of x. In y2, we have sine x. So you will see first the graph of the first 4 terms, which is a polynomial, and then you'll see the thick line coming, and you'll see where it approximates sine and where it does not. Let's go ahead and graph. And here comes the polynomial through the x-axis. It turns back through the y-axis, and it turns again. Very nice polynomial picture. Notice that sine sort of joins up and then goes away. In fact, right over here, sine and the power series approximation are identical. Over here, and everything in between, the sine is a very good approximation of, very well approximated, by the power series. But if you wanted the sine of a number over here, or a number over here, that would not do you very much good. You'd have a lot of error. And notice that we were wanting the sine of 30 degrees. 30 degrees would be right over here, and of course that is in an area where the sine and the power series agree. So we can see how the power series was very useful in approximating values of much more complex functions before the advent of computers and calculators. So we can see that calculus not only created a means of measuring change, but also the integral was created, which allows us not only to find areas between curves, but actually to find the summative effect of change. And with the use of the power series in calculus, we can approximate functions using a polynomial. This concludes our 2 lectures on calculus. Lecture 12, which is next, will examine the beauty of fractals. Do not miss it.